Hello friends, we are discussing the view factor between two finite area surfaces. In the previous class I discussed the definition of the view factors and applied the area integration technique to find out view factors between two parallel plates. In this lecture we will do a couple of examples and I will introduce you a new method, Hotel cross string method, for the evaluation of view factors. The first problem that we are going to solve in this lecture includes two flat circular plates. The plates may have same area or they may have different area. So, in this case we will take that the radius of the two plates is different, they are parallel separated by some distance h. We will apply the contour integration technique to find out the view factor between these two plates. So, as we have already developed, the expression for the view factor between surface 1 and 2 is given by, as per the Stokes theorem, we have already done that, 1 upon A1 and then double line integration over surface 1 or path 1 ds1 and ds2 ln s, where s is the separation distance, ds1 dot ds2. So, this is the expression for finding out the view factor between the two configuration. If you just look at the problem, let us understand the coordinate system used. So, we have x direction, y direction and z direction is pointing upwards. Okay. So, n1 vector is basically equal to the k cap and n2 vector is equal to the minus k cap. Now, with this notation, because the two normal vectors are pointing in opposite direction, the azimuthal angle, the way it is measured, the psi 1 will vary from 0 to 2 pi, while psi 2 will vary from 0 to minus 2 pi. It is just the bookkeeping thing. The angle psi 1 varies from 0 to 2 pi and psi 2 will vary from 0 to minus 2 pi. Okay. So, first of all we try to find out ds1 and ds2 in terms of the coordinate system. So, we can easily write x1 is equal to r cos psi 1, and because we are doing line integration we take just r value to be r1, where r1 is the radius of disc 1. Okay. So, x1 anywhere on the path or contour or periphery of the disc will be simply r cos psi 1. Okay. And similarly, y1 will be equal to r1 sin psi 1. Okay. So, we can write ds1 as equal to r1 d psi 1 minus sin psi 1 I cap plus cos psi j cap. This is all vector. So, any point on the disc periphery of disc 1 can be represented the vector along that path as ds1 is equal to r1 d psi 1 is equal to minus psi 1 I cap plus cos psi j cap, where I cap and j cap are unit vectors in x and y direction respectively. Similarly, we can write ds2 as equal to r2 d psi 2 minus sin psi 2 I cap plus cos psi 2, that is called this psi 1 j cap. This is ds1 and ds2. Now, the dot product between these two, ds1 dot ds2. So, ds1 and ds2 are also vector quantities, will simply be equal to r1 r2 d psi 1 d psi 2 sin psi 1 sin psi 2 plus cos psi 1 cos psi 2, and this can be simplified as r1 r2 cos psi 1 minus psi 2 d psi 1 d psi 2. This is the dot product of path vector S1, ds1 and ds2. Okay. Now, S, the distance between 2 points at peripheries of disk 1 and disk 2 is simply written as x1 minus x2 square plus y1 minus y2 square plus z1 minus z2 square. Now, z1 minus z2 is simply h. So, we can just write this as x1 minus x2 square plus y1 minus y2 square plus h square. Okay. And this can be simplified if we put the value of x and y, this can be simplified as h square plus r1 square plus r2 square minus 2 r1 r2 cos. Okay. So, this is going to be, and then we have to take under root. Okay. So, this is going to be the distance between two disk points of two disk. So, this is disk 1, any point on this disk and any point on this disk separated by a distance s will have this value, s is equal to root h square plus r1 square plus r2 square minus 2 r1 r2 cos psi. Now, the view factor f122 is simply equal to as per this definition 1 upon a1 ln s ds1 ds2 will simply be equal to r1 r2 2 pi r1 square 0 to 2 pi, this is for psi 1, and psi 2 will vary from 0 to minus 2 pi as already told, ln h square plus r1 square plus r2 square minus 2 r1 r2 cos psi 1 minus psi 2, and we have to take power half. Okay, because this is a, and then cos psi 1 minus psi 2 d psi 1 d psi 2. Okay. So, this is going to be the expression for view factor. Okay. Now, it looks very terrific, the integration looks very terrific. Okay. Those who are expert in mathematics can solve this integration very easily. There are integration tables available. One thing that one should observe is this integration can be simplified very easily, because the only thing that appears as a variable is basically the difference psi 1 minus psi 2. Okay. Nowhere we have psi 1 and psi 2 appearing independently in this integrand. Okay. So, we can basically integrate this easily. So, we write f12 as equal to minus 1 upon pi r2 by r1. Okay. Just integrating and change of variables. So, we write psi 2 is equal to psi 1 minus psi, or we write psi is equal to psi 1 minus psi 2, just a change of variables we have done. So, we just reduce this integration from double integral to single integral like this, h square plus r1 square plus r2 square minus 2 r1 r2 cos psi, and this will be the half cos psi d psi. Okay. So, by changing this substitution, we have just reduced the level of order of integration by 1, and this will be solved using integration by parts. I will just write down the steps here, r2 by r1 sin psi ln h square plus r1 square plus r2 square minus 2 r1 r2 cos psi minus r1 r2. So, we just apply the integration by parts. h1 plus r1 square plus r2 square minus 2 r1 r2 cos psi, and this basically reduces to r2 by r1 upon 2 pi 0 to 2 pi sin square psi d psi x minus cos psi, okay, where x is equal to h square plus r1 square plus r2 square upon 2 r1 r2. So, now again we have one more integration to solve, but this integration is relatively easy to solve, and what we get as a final result for the view factor is r2 by r1 upon 2 pi into 2 pi x minus root x square minus 1 is equal to r2 by r1 x minus root x square minus 1, okay, where x is the having this value. So, this is how you can apply the contour integration technique to find out complicated view factors between standard plate configurations. Okay. Now, we will do one more problem. Okay. This problem basically involves simple algebra, view factor algebra. We have already discussed this algebra, that means summation of f I j, j is equal to 1 to n is equal to 1, okay, and a I f I j is equal to a j f j I. So, these are the rules for view factors that we have studied. We apply these rules to find out the view factors between this configuration 3 and 4. Okay. So, we have to find out the view factors f 3 and 4. Now, when we solve this problem, we assume that the view factors adjacent plates are known, that means we know f 1 2, this is known. We know that f 1 plus 3 to 2 is known. Okay. So, these are adjacent plates, they may have same area or they may not have same area. So, by assuming that the view factors for the adjacent plates are known, we can find out the view factors between non adjacent plates 3 and 4 using this view factor algebra. So, we write f 3 to 4 as equal to f 3 to 2 plus 4 minus f 3 to 2. Okay. This is simply the summation rule. Okay. F 3 to 4 is equal to f the entire vertical plate 2 plus 4 minus f 3 to 2. Okay. Then we write using the reciprocity theorem. Okay. So, we write f 3 to 4 as 1 upon a 3 a 2 plus 4, a 2 plus 4 means a 2 plus a 4, and f 2 plus 4 to 3. Okay. This is the first quantity on the right hand side. Then minus similarly this one we can do a 2 f 2 to 3 divided by a 3. Okay. So, we have used both the summation rule and the reciprocity theorem to find out f 3 to 4. Okay. Now, f 2 plus 4 to 3 is also not known. So, let us again look at these quantities. Okay. So, f 3 to 4 is equal to the first quantity becomes a 2 plus a 4 divided by a 3, and the first quantity becomes f 2 plus 4 to 1 plus 3 minus f 2 plus 4 to 1. Okay. So, this is the first quantity, and then second quantity minus a 2 by a 3 f 2 to 1 plus 3 minus f 2 to 1. Okay. Just let me just show you f 2 to 3. So, f 2 to 3 is equal to f 2 to 1 plus 3 minus f 2 to 1. Okay. So, these quantities, so we have now unknowns or rather knowns f 2 plus 4 to 1 plus 3, f 2 plus 4 to 1, f 2 to 1 plus 3 and f 2 to 1. So, all these quantities as we started with are known. Okay. These values are available at the back of the book, you can easily read these values. Okay. and based on this view factor algebra we could find the view factor F324 for the plates which are not adjacent to each other. Okay. Now, we will discuss the other method, the Hotel cross string method. This method is very powerful and very simple in calculating the view factors. The only condition is that it is restricted to 2-dimensional enclosures. That means the surfaces for which the view factor is being calculated have to be infinitely long in the third dimensions. Okay. For these type of surfaces we can calculate the view factor using the Hotel cross string method. Okay. Now, the surfaces may be flat or they may have irregular geometry. For example, we want to calculate the view factor as shown in this figure. The surface A1 is also irregular and surface A2 is also irregular. So, how do we find? What we do in this method is we put 4 pins. Now, these pins are called A, B, C, D. Okay. These pins, 2 pins are on the surface A2 and 2 pins on the surface A1. Okay. And we put a wire or the thread. Okay. Now, we call it string because the method is called cross string method. So, we have this one string AC, okay. Another string is tied between A and D, similarly A and B, C and D and C and B. Okay. So, so we have put 6 strings, okay. Total 6 strings are put, okay, and these strings are assumed to be tied to each other, tied to the pins. They are tight and they are convex in shape. Okay. So, once we have this, we assume that the strings are representing basically an imaginary surface. So, for example, string AC, you can think of it as a surface that is extending in the third direction. So, you just assume it to be a surface. So, just by measuring the length of these strings, the method can calculate the view factors. Okay. So, the method does not involve any complex mathematics. It basically needs some measurements of the string lengths, which for standard configuration is pretty easy, and it needs some view factor algebra. So, what we do is we have the summation rule. The summation rule is applied to the various view factors. So, for example, the triangle ABC, triangle A, B and C, we have this surface AB. Okay. So, FAB to AC plus FAB to BC, then FAB to BC, so BC is this length, and FAB to AC is equal to 1 or AB. Okay. We have multiplied by area AB throughout. Okay. FAB to AB is 0 because the surfaces are convex. Okay. So, FAB to AB is equal to 0. So, we have applied the summation rule here. Similarly, we apply the summation rule to surface AC and surface BC. Okay. So, we get 3 equations by applying the summation rule to the 3 sides of the triangle ABC. Okay. Similarly, what we do is we apply the method to the triangle ABD. Okay. We apply the method, similar method to triangle ABD. Okay. Now, we so in this 3 equations we have 6 unknowns and we have only 3 equations. Okay. So, we need some more relations, and these relations are basically found using the reciprocity theorem. Okay. So, reciprocity theorem basically we replace these view factors in red. Okay. So, for example, in the equation we have FACAB. So, we have replaced it with the FABAC. Okay. Similarly, we have replaced these 3 view factors using the reciprocity theorem. Now, these 3 equations we have 3 unknowns and 3 equations. So, we can use a simple algebra to solve this, and what we get is the view factor AB to AC is equal to area AB plus area AC minus area BC divided by 2 area AB. Okay. And same thing we do in the triangle ABD. So, we get view factor FAB to BD as area AB, area plus area BD minus area AD divided by 2 area AB. Okay. So, just by applying the summation rule and reciprocity theorem to the 2 triangles, we have calculated the view factor, okay, ABAC and ABBD. Okay. Now, again we apply the summation rule to the triangle. Okay. So, we have ABCD quadrilateral, we apply the summation rule and we get another relation FAB to AC plus FAB to BD and FAB to CD is equal to 0. Again FAB to AB is equal to 0. So, we again apply the summation rule. Okay. Now, this time not to the triangle, but to the quadrilateral, and the expression for FAB to BD is already found, FAB to AC is already found. So, these two expression we have already found. Okay. Now, we basically solve for ABCD. Okay. This is the unknown here, and when we put the values of FABAC and FABBD in this relation, we can simplify this. Okay, FABCD. So, all the view factors are now known. Okay. So, between FABCD, okay, what is let us look at it, what is ABCD. So, ABCD is this surface and CD is this surface. Okay. This does not represent the actual surface, this represent the string surface over this real surface. Okay. So, we have found the view factor FABCD represented by imaginary stringed surface, okay, over the real surface. Okay. Now, we have to convert this view factor to the real surface. Now, the argument here is that whatever radiation leaving AB, all the radiation leaving AB that falls on surface CD will actually go to surface A1, right. So, we have radiation emitted from surface AB falling on surface CD, the string surface, and the string surface is tied in such a way that all the radiation that falls on CD will actually fall on A1. Okay. So, based on this argument FABCD is equal to FAB1, okay, and then applying the reciprocity theorem we write FAB1 is equal to A1 upon A1 AB and F1 AB. Now, similar arguments hold true for this surface, all the radiation leaving surface A1 and travelling to surface AB will actually fall on A2. So, we can also write F12 AB as F12. So, by using this reciprocity theorem we have related FABCD to F12, and the relation is basically FABCD is equal to A1 upon AB F12. Okay. So, finally, we get F12 is equal to, substituting the value of this expression in this relation. Okay. So, we put the value of FABCD in this expression, we get F12 the view factor as ABC plus AD, which are the basically diagonals. So, sum of diagonal lengths. So, you have to measure or you should know the length of the string in the diagonal direction minus AC plus ABD, which is the sides of the quadrilateral. Okay. So, you should know the sides, okay, either by measurement or by standard configuration, and then 2 divided by A1. A1 is the originating area. So, this is the Hotel's cross string method. As you see that this is a very simple method, just by using the view factor algebra, summation rule and the reciprocity theorem, we have calculated the view factor between two surfaces which are not represented by any mathematical relation, which are complex in geometry. Okay. Now, to demonstrate the power of this method, we will solve the same problem that we solved using the area integration method, and we found that area integration method involves complicated integration and algebra. Okay. So, we will solve this problem using this method. So, we have again as shown two plates, the width of each plate is W and the separation distance is basically the H. Okay. This is a simple configuration for this method, but complicated problems can be solved easily. So, what we do is we put 4 pins, pin A, pin B, pin C and pin D. Okay. So, we have put 4 pins, then we tied 6 strings, one string, another string. Okay, let me just put it using a different color. So, this is one string, this is another string, this is one string, this is another string, and 2 string will be just parallel to the plates. Okay. So, these 6 strings we have put. Okay. So, the diagonals have AD and BC have same length, okay, and the length is basically given by root, this distance is h and with w. So, h square plus w square. Okay. This is the length of the diagonals, and the sides AC is equal to BD is simply equal to h. Okay. Now, as per the formula F12, this is surface 1, this is surface 2, F12 is basically equal to diagonal minus sides divided by 2 times A1, okay, where A1 is simply equal to W, okay, assuming the depth of the plates in the plane of the board is 1. Okay. So, diagonals is equal to root h square 2 times h square plus w square minus 2 times h divided by 2 times w. Okay. So, 2 will cancel out from the numerator and denominator. So, we get F12 is equal to root h square plus w square minus h upon w, and this becomes equal to root 1 plus h by w square minus h by w, and this is equal to 1 plus h square, root 1 plus h square minus h, and h is equal to h by w. Okay. So, we have already found this expression using the area integration method that involved complicated double integration, and the expression that we found for the view factor, if you can recall, was similar, root 1 plus h square minus h, where h is the ratio of the separation distance divided by width of the plates, and this method can very easily give you the view factors for complicated geometries as well. So, the method is very powerful, with the only limitation that the plates have to be infinite in depth. If you have finite length plates, the method may not be applied. Okay. So, thank you very much. This basically concludes one important topic on view factor evaluation. We still have a number of methods for the evaluation of view factors, namely the inside sphere method and the Monte Carlo method, that we will take in the subsequent chapters. Thank you.